So next presenter is Dr. Luigi Di Palma from the SeeQc company. The name of the title of his talk is Quantum Technologies at SeeQc. Please.
Good afternoon. My name is Luigi Di Palma, and I am a quantum engineer at SeeQ. The title of my presentation is Scalable Energy Efficient Quantum Computing. And I will show you the activities and the research that we do at SeeQ. Okay, so I would like to start the presentation with these two pictures. So on the left, we have the ENIAC, which is the state-of-the-art classical computer in 1946. This is the first full-stack computer. And on the right, we have the state-of-the-art of quantum computer in 2023. So, these two pictures looks very similar because we can say that at the moment, the state-of-the-art of quantum computation is very similar. Our quantum system are very close to what the classical computers in 1946 looks like. We can, in this picture, on the one on the right, we can recognize three different elements, if you want. We have the fridge, which is the gold structure, with a lot of cables, filters, and so on. At the bottom of this fridge, we usually have a chip, which is our quantum computer. And behind the DR, the dilution refrigerator, the fridge, or whatever you would like to call it, we have the electronics to control the state and read out the state of the quantum chip. So as you can see, for at the moment, in order to measure and set the state of quantum computers, we need a lot of instruments at room temperature, which are connected by very long cables. This is not a scalable approach, especially if one would like to build a general purpose quantum computer. We have understood from the presentation of today that in order to have a very general purpose quantum computer, we need at least 1 million of qubits, which means that this approach is not feasible. We cannot build a general purpose quantum computer using the technique that we are using now. So, okay, in the past, for classical computation, a big improvement has been realized when the electronics has been, included in a unique microchip, which is the picture on the right. And we in SeeQ, we believe that the goal, the way to proceed, the way to build a general purpose quantum computer is to transfer all the electronics at room temperature inside a single chip. And that's what the goal of the company. So the goal of the company is to transfer all the electronics that you see behind the dilution refrigerator in a unique chip. This approach has multiple advantages. First of all, we can scale up the number of qubits because we don't need all the components that actually today you have at room temperature. Also, this approach is very advantageous from an energetic point of view because now, because everything is very is scaled in a micrometer size, and so the power dissipation is very, very low. And also, in this way, you can also reduce the latency and the heat load, the heat that comes out from the room temperature. So in SeeQ, we believe that this is the way to go. And this is how we envision a quantum computer in the future, a quantum chip in the future. You can see that the system is composed by different layers. The top layer is the qubit layer, where you can, for example, take in consideration any leading platform from any company. And on the bottom, you have other different layers, other different chips. And on this chip, we host our control and readout technology. This technology is based on SFQ. SFQ means single flux quantum, but basically it's a classical electronics based on superconductors and Josephson junction. This means that using our control and readout system, we can reduce the power consumption, we can enhance the speed of our operation, and also we can improve the scalability. And here, just for you, I have an example of one of our chip. And I know that it's, it's very, very far from you, but you can see that there are some, a chip with a planar system, a bottom layer, and also a top one, which is the qubit part. So SeeQc is a startup based, the headquarters is in New York, but we have also some laboratories UK and in Napoli, which we have a lab in the University Federico II. But SeeQc has also a lot of collaboration with other universities and companies, as you can see from this map. Okay, now I would like to focus on our activity in Napoli. And I would like to mention that we have a joint lab with CESMA at Unina, where we host our deletion refrigerator. But also we have active projects and collaborations with the university, the Department of Physics at the University Federico II, guided by Professor Francesco Tafuri and Giampiero Pica. I also would like to mention that we have been the first to demonstrate the first Italian full stack quantum computer in the 2023. Full stack means that the quantum computer is not only the hardware, but also the software and the cloud to run the algorithms remotely. And this has been done in 2023. In Napoli, the main activity is based on develop a device for read out the state of the qubit. The state of the qubit is a very fragile system, as you know. We can build a qubit from different type of platform, superconducting, ion trap, cold atoms, and so on, photons. But what all these platforms have in common the fact that the state of a qubit is very fragile. We need to protect the qubits, and the readout is a very delicate operation. In SeeQc, and in particular in Napoli, we have developed a system on chip able to read out the state of the qubit. This system is based on the device on the right, which we call Josephson Digital Phase Detector, or JDPD. And basically, this is a phase detector. It's a device capable of reading the phase of a microwave tube. In this way, we can read out the state of the resonator, which typically in superconducting qubits is coupled to qubit transfer, for example. There are many advantages of using this approach, the JDPD approach. First of all, this device can be hosted inside the fridge, and we can perform all the operation with low latency, with small power, very, very small power dissipation. And also the output of our device is already digital. We don't need any type of down conversion, for example, that today is performed at room temperature. Also, it's possible to integrate multiplexing. And actually, there are two possible configurations that we can adopt in order to use our device. The first configuration is the MCM1, which is the picture on the bottom. And basically, this is very close to what I have already shown. So we have a planar chip with the quantum computer, with the JDPD or the control electronic. And on the top, we have the quantum chip. But there is also another very interesting approach for using our readout device, which is the co-package configuration. In this case, the quantum chip, for example, from another company could be hosted on the same sample order. And this is very interesting because everyone can send us, or we can send our JDPD to them, and they can host everything on the same, inside the same sample order. It's done. They don't need to modify anything from the layout point of view. And today we are able to achieve performance, fidelity of 98.2%, which is very close to the state of the art. Of course, this is a research project, so we are still in developing. But you know, it's a very interesting results, and we believe that this is the way to go in order to build a general purpose quantum computer. And yeah, on the right we have the typical Rabi oscillation, which is a very common experiment that you do in quantum computation. And the state of the qubit in this case is measured by our device, our JDPD. So yeah, I think this is my last slide. Hope I give you, a landscape of all our activities, and I hope to receive questions from you and comments. Thanks.
Thank you very much. Thank you very much. We have time for questions and comments, please.
Thank you. I have a question about power dissipation. If you integrate your SFQ circuit at the same level of the qubit, we know that currently SFQ circuits they dissipate much less than semiconductor, but they still dissipate quite some power because of the resistors which are inside. Do you have plans to go? And I know that the low energy variants are much lower than the current one. So what's your approach in this direction?
Okay, yeah, it's a good question. You know, there are, as you mentioned, there are different approaches for develop inside the fridge technology to drive and read out the state of the qubit. One of these is the SFQ, which is the approach that we are actually following. And the SFQ devices have a very low power dissipation. We are talking about something around 5 femtowatt, which is very, very low. And there are a lot of papers in literature in which the drive, for example, the qubit, but in this case also the readout, is demonstrated without any back action from heating generated by the SFQ devices. I also would like to mention that our structure is very helpful in this direction, because having 2 different layers or multiple layers of chips could help us to further reduce the effect of the SFQ devices on the quantum chip. So, you know, to summarize, at the moment we don't, but not only us, but other research group in the world, they don't see any type of back action or any type of heating effect generated by the SFQ devices. Of course, there is other approaches, like, for example, the cryo-CMOS, but the cryo-CMOS are very, very, you know, the power dissipation is very, very high in that case. And so for that reason, they typically host this type of electronics at 4K, where the cooling power is higher. Thank you for the question.
Another question, comments? I have some short question. Maybe I don't understand well. When you told about the converter of the qubit signal to the digital signal, yes?
Yes.
One condition on your slide was all the signal are generated internally. Can you clarify this?
Yes. You mean this slide?
Yes, yes.
Yes, exactly. Yeah, the idea of SeeQc is to transfer all the devices that actually use at room temperature inside the fridge. Of course, we have a roadmap. We are proceeding step by step. At the moment, the readout is performed in this way. The JDPD is hosted on the chip inside the fridge. The signal are generated outside at the moment. but in the future it will be different. So the signal that you have in this slide are basically the signals that we are generating outside, and they probes the state of the resonator, and we measure them with the GDPD. Regarding the microwave generator inside the fridge, there are different approaches. One, for example, could be using SFQ oscillators, ring oscillators, for example, that are very close as the classical ring oscillators that we have in classical devices. But also there are other type of technologies compatible with this type of devices that could be adopted.
Okay, thank you very much. Okay, thank you very much again for your research and talk.